Welcome. This video is going to talk about the concept of specific heat. Specific heat is defined as the amount of heat required to raise the temperature of 1 gram of any substance by 1 degree Celsius. So this means each substance has its own specific heat value. And if you know the identity of the substance, you can probably look up the value quite easily because someone else has found it experimentally. Or you could go ahead and determine the value yourself experimentally, which we'll talk about later. You may have noticed specific heat has a funny abbreviation. It's C, but that's because it's also known as specific heat capacity. Capacity being how much heat it can hold. So when we talk about specific heat values, metals are things that tend to heat up quickly and cool down quickly. So they have a lower specific heat value. It doesn't take a lot of energy to get a metal to heat up. You put a metal spoon into your hot cup of coffee and it quickly becomes warm itself. But things like water, glass, ceramic, they tend to heat slowly and then they also cool slowly, so they have higher specific heat values. But we usually think of materials as being good conductors or good insulators. But what we're really thinking of is that good conductors are good conductors because they have low specific heat values. And good insulators are good insulators because they have high specific heat values. So high and low specific heat is really about how well it heats up and cools down. That would be a good conductor or low specific heat. Or how well it holds heat, which would be high specific heat. So some examples of where you see specific heat every day is, if you ever notice on a really hot day, the dark green grass will be cooler to walk on than the white sidewalk. And from what we know about colors, just the opposite should be true. But it's all about specific heat. The white sidewalk has a low specific heat, so it heats up quickly and gets hot, but it'll also cool down quickly when evening comes. But the dark green grass, because it has so much water in it, is going to be much slower to heat up. This also explains why a bagel takes so long to toast and then it stays so hot for so long afterward. But white bread, it burns quickly in the toaster and it cools just as quickly. Or another example is what they call the moderating effect of lakes on weather. And this is the idea that if you have a city near a lake, like Duluth in Minnesota, it tends to be cooler in the summer and warmer in the winter. That's because that big lake doesn't change its temperature that much between winter and summer. So how do we calculate specific heat value and why do we care? Well, when we're making bridges, roads, buildings, any structure like that, gaps have to be left between the beams for expansion and contraction of the materials. Because during heating and cooling, the materials are going to expand and get bigger, and cooling, they're going to contract and get smaller. And the amount of expansion and contraction not only depends on the weather for that area, but it also depends on the specific heat. Does it absorb a lot of energy or not absorb a lot of energy? That helps engineers calculate how big the gap must be. So next time you're out driving, when you get to an overpass on the freeway, don't stop obviously, but when you feel the car do the cha-chunk as it hits that gap, now you know why the gap is there. To calculate the specific heat, you need to know the mass of the substance, you need to know the temperature change in this substance, and you need to know the amount of heat released. So the basic equation is delta H, which means change in heat, or you could just put Q, although I'd say it's more common to use delta H, equals, and I like to think of this as MCAT, mass times specific heat times change in temperature. So the unit for specific heat seems a little strange. It's joules per gram Celsius degrees because it just combines the unit for mass, temperature, and specific heat. And so the unit really defines specific heat for you. It's the joules needed to raise 1 gram of the substance 1 degree Celsius. So let's look at a couple examples here. My first example says a 55.6 gram sample of material changes temperature from 75 degrees to 60.2 degrees when it loses 3,080 joules of heat. what is the specific heat of this material? So if I look at my equation, I'm being asked to find C. Have I been given the other 3 units? Yes, I can find the other 3 variables in this problem. Delta H was given to me as 30,080 joules, and I'm going to include units so you can see how they cancel out here. The mass is 55.6 grams. C is what I'm trying to find. And the change in temperature, if I just do some quick math on the side here, the change in temperature is 14.8 degrees Celsius. So solving for C, I need to divide both sides by 55.6 times 14.8 to get C isolated alone. And so now when I go ahead and plug and chug, 3080 divided by the product, so use your parentheses, 55.6 times 14.8. This gives me a specific heat value of 3.74. And none of those units cancel, so that means my final unit is joules per gram per Celsius degree. My second example says a 12.5 gram sample of a metal with a specific heat of 0.214 absorbs 37.7 joules of energy when placed in boiling water. If the starting temperature of the metal was 25 degrees, what's the final temperature? Now, I included this example because this one tends to give people trouble, and it really isn't that difficult. I have delta H equal to M times C times delta T, or MCAT, and I like to keep it simple. I have 37.7 joules as delta H. I have a mass of 12.5. I have a C value of 0.214. I don't know delta T. So I'm not going to try and solve for the final temperature right now, and I'm not going to include that 25 degrees because that just makes this messy. This equation asks for the change in temperature, so it can also help me find the change in temperature. So if I divide both sides by the 12.5 times 0.214, when I solve for delta T, I have a temperature change of 14.1 degrees Celsius. Now I can look at my starting temperature was 25 degrees. My ending temperature is what I want to know, and my temperature change was 14.1. It's also important to think, did this temperature increase or decrease? Since the temperature was increasing, it absorbs it. This is a positive temperature change. If it had lost it, that would be a negative temperature change. So now that means my final temperature had to be 25 plus the 14.1, or 39.1 degrees Celsius. So I've got a couple examples for you to try, so I'd encourage you to pause and try this on your own. A 500-gram piece of concrete reached a temperature of 74 degrees Celsius during the day, cooled down to 40 degrees at night. How much heat was released if concrete has a specific heat of 0.84 joules per gram Celsius degree? Now, if the specific heat value isn't given to you, you just need to look up the value for the identity of the material. And you can find charts for this in your textbook. You just Google it online, specific heat values, not difficult to find. So again, I'm using the same equation, delta H equals MCAT. And I'm being asked to calculate the heat, so I'm trying to find delta H. So this one's going to be pretty straightforward. I'm just going to have 3 numbers to multiply together. 500 grams times 0.84 times my change in temperature, and again, if I take 74 minus 40, I see I have a temperature change of 34 degrees. And when I plug and chug 500 times 0.84, excuse me, times 34, I come up with delta H equal to 14,280. What's my unit? Well, remember 500 is grams, 0.84 is joule, grams, Celsius, degrees, and this was degrees Celsius. So you notice that the grams cancel, the degrees Celsius cancel. So this label is joules, or if you want to, you could convert it to kilojoules, which is often done. It'd be about 14.3 kilojoules. Here's a second one for you to try. A sample of iron with a mass of 10 grams changed from 50.4 degrees to 25 degrees and released 114 joules of heat. What's the specific heat? So again, delta H equals MCAT. So when I plug in here, I have 114 joules. I have 10 grams. C is what I'm hoping to find. And my change in temperature, 50.4 minus the 25, is going to give me 25.4 for my temperature change. So when I solve for C, divide each side by the 10 times 25.4 to make units cancel out. C is going to be equal to, remember this is grams, degrees Celsius, so I take the 114 and divide by 10 times the 25.4, keep that in parentheses. I come up with 0.449, and my unit is that strange unit, joules per gram per Celsius degree.